Okay, so today we're diving into something you probably have under your kitchen sink. We're asking if this common chemical could actually be the key to cleaning up one of the world's biggest industries. We're talking about ammonia, and whether it could really be the future fuel for global shipping.
All right, so first things first, let's talk about the biggest argument for using ammonia as a fuel. And honestly, it's going to surprise you. It's all about safety. Specifically, we're looking at why this stuff is actually pretty hard to set on fire.
Okay, to really get this, we gotta break down a couple of key ideas. The first one is flashpoint. This is basically the lowest temperature where a liquid gives off enough vapor that it could be ignited by something like a spark. For ammonia, that temperature is a pretty high 132 degrees Celsius. I mean, that's way hotter than boiling water, which makes it surprisingly tough to just light on fire, especially out on the open deck of a ship.
But here's where it gets really interesting. It's not just about heat. You also need the perfect mix of fuel and air. This brings us to the lower flammable limit, or LFL. Think of it as the absolute minimum amount of ammonia vapor you need mixed in the air for it to even have a chance of catching fire. Any less than that, and the mixture is what they call too lean. Basically, not enough fuel to get the party started.
And on the flip side, you've got the upper flammable limit, the UFL. This is when you've got too much fuel floating around. The mixture becomes too rich, and there's just not enough oxygen to feed a fire. It's kind of like flooding an old car's engine. It just won't go.
So what this all means is that a fire can only happen in this super specific window between those lower and upper limits. This little sweet spot for ignition is called the flammable range.
And check this out, because this really drives home ammonia's biggest safety feature. Its flammable range is incredibly narrow, from just 15% to 28% concentration in the air. This means if you have a leak out on the open deck of a ship, those vapors are probably going to spread out so fast that the mixture just becomes too thin to burn, almost instantly. I mean, that's a huge, huge plus.
But okay, here's the catch. The very same thing that makes ammonia so safe, the fact that it really doesn't want to burn, well, that's also its biggest engineering problem, right? Because how do you make it burn reliably when you actually need it to, like inside a giant ship engine? Let's dig into that.
So to get our heads around that, we need to talk about another key concept: auto-ignition temperature. Now, this is totally different from the flashpoint we just talked about. This is the temperature where something just gets so ridiculously hot, it just bursts into flame all by itself. No spark, no flame, nothing.
1 degree Celsius. I mean, that is just incredibly hot. It needs a ton of heat before it'll just combust on its own.
So what's that actually look like in a ship's engine room? Well, on one hand, it's pretty good news. A little leak near a hot steam pipe, probably not going to start a fire. But, and this is a big but, if you have a high-pressure leak right next to something super hot, like the engine's exhaust manifold, that could be a total disaster, an instant fire, if that fuel-air mix is just right.
So you see the problem here, right? If a fuel fights you this hard on burning, how on earth do you build an engine that can reliably light it on fire thousands of times a minute to push a container ship the size of a skyscraper across an ocean? It's a seriously tough nut to crack.
All right, but the headaches don't stop there. Let's just say you figure out the whole ignition problem. Now you're staring down an even bigger issue, a logistical one. Just how much ammonia you have to lug around. Okay, so to get this, we have to look at something called the fuel's lower heating value, or LHV. Now, forget all the complicated science for a second. All you really need to know is that LHV is the real-world usable energy you get from a fuel. It's the bang for your buck in an engine.
And wow, this chart really puts the problem into perspective. Look at that. A kilogram of ammonia has less than half the energy of the heavy fuel oil or diesel that ships use today. It just doesn't have the same oomph.
So you've got this low energy content, and on top of that, liquid ammonia isn't as dense as regular fuel either. So when you crunch the numbers on both of those things, you land on one single massive number: 4.
And here it is, the punchline. To go the exact same distance, a ship running on ammonia would need fuel tanks that are 4 times bigger.
What?
Now think about that. In an industry where every single square foot is for paying cargo, giving up that much space just for fuel, that's a gigantic economic and design nightmare.
So where does all this leave us? Well, ammonia is this really fascinating puzzle, isn't it? It could be a way to get to zero carbon shipping, but man, that road is filled with some pretty serious potholes.
Yeah, it really all boils down to this fundamental trade-off. The exact same things that make it safer if there's a leak, the fact that it's so hard to burn,
are the very same things that make it a huge pain for engineers. It's tough to ignite in an engine, and it forces ships to have these enormous, inefficient fuel tanks.